In this video, we're going to talk about shear and bending moment functions and diagrams. So to start off, we're going to consider a beam that's subjected to an arbitrary distributed load and a series of concentrated forces and moments. So we have our arbitrary distributed load, and we would say that the distributed load would be considered positive when acting upwards. Right, so our distributed load is defined by omega of x. And then we also have a series of point loads that we'll just define as F1, F2, F3, and then also some point moments or some concentrated moments that we'll define as M1 and M2. Now, what we'll do is we will consider a free body diagram of a segment of the beam that has a length delta x. So we'll draw that free body diagram below, right? So again, the length of that segment is delta x. We will assume that that segment does not contain any point loads. So let's just, for consistency, let's just move the F2 so that it doesn't lie within that delta x. And so we'll assume that the internal shear forces and bending moment are acting in the positive direction. I did an earlier video on the sign convention for shear forces and bending moments. So if you're unfamiliar with the sign convention, you might want to take a look at that. We're also going to replace the distributed load by a concentrated force that we will call omega times delta x. Right, so let's just draw in what would have been the concentrated load, and remember that is defined by omega as a function of x. And so we've increased the shear force and moment on the right end by a small finite amount to make sure that the segment is in equilibrium. The other thing that we're going to do is we're going to specify the distance from the resultant point load to the edge of the segment. We're going to call that alpha times delta x, where alpha is less than 1. So now what we're going to do is we are going to apply the equations of equilibrium to the free body diagram. So we will start with sum of forces in the y direction. So we know that the sum of forces in the y must be equal to 0. So based on that, we get this equation. And if we solve this equation, we get delta v is equal to omega times delta x. Then we can take sum of moments about point O, which we did not specify, but we'll do that now. So we will call this point at the right end and mid height of the segment, we'll call that point O. And so we'll take sum of moments about that point, and we get the following equation. And if we solve that equation, we get delta M is equal to V times delta X plus omega alpha delta X squared. Now, based on delta X being considered an infinitesimal length, we will assume that delta X squared is equal to 0. So the right part of the bending moment equation is going to go away. And then so we have two equations here, right? We have this one and we have this one. And so if we take both equations and we divide by delta X, and then we take the limit as delta X tends to 0, we will end up with the following equations. Right, so the one on the left, which is derived from this equation, says that the slope of the shear function is equal to the intensity of the distributed load at a particular point. So here we have, this is the intensity of the distributed load. And this would be the slope of the shear force function. And then on the right, we see that the slope of the moment function is equal to the shear force at a particular point. The next step is we're going to take these two equations and then we're going to integrate them between 2 points. And what we get is that delta V is equal to the integral of omega dx, which basically says that the change in shear between any 2 points on the beam is the same as the area under the loading diagram between the 2 points. So the change in shear, and this integral is the area under the distributed loading diagram. And if we do the same for the other equation, we get this expression, which basically says that the change in moment between 2 points is equal to the area under the shear diagram between the same 2 points. Now, we should keep in mind that these equations cannot be used between 2 points where there's a concentrated load or moment, because they would not account for the sudden change in shear or moments at these points. So to consider these cases, we will take a look at a free body diagram for a differential element that has a concentrated load or a concentrated moment. So let's start with the concentrated load case. Again, the length of this differential element is delta x. Let's call the concentrated load F. And we'll draw the shear force and bending moment over the segment. And then we'll do the same for the concentrated moment case. And we'll apply the concentrated moment at the center. And we'll define our point O as we did before in the center right part of the segment. So from the free body diagram on the left, we see that when the force F is positive, then the change in shear force is also going to be positive. Similarly, if the shear force, if the force F is negative, the change in shear force is going to be negative. And in the figure on the right, we see that if the external moment is clockwise, then delta M will be positive and vice versa. And we can also come to that conclusion by taking sum of moments in the y direction for the case on the left, and that would lead us to delta V, or the change in shear force, is equal to F. And for the case on the right, if we take sum of moments about point O, we get delta M is equal to M, where, well, actually our applied moment, we'll call it M star, right? Because we're already using M for the moments at the ends of the segment.